Have you ever wondered what a secret meeting in 1930s Rome has to do with a modern supersonic jet? Well, the answer is a kind of hidden language, a language that unlocked the physics of flying at unbelievable speeds. Today, we're going to decode that language and see how thermodynamics became absolutely essential for high-speed aviation.
So here's how we'll break it down. We're going to start with a pivotal meeting that basically dreamed up the future of flight. Then we'll get into the nitty-gritty of why all that speed creates so much heat. After that, we'll open up the aerodynamicist toolkit, cover the 2 unbreakable rules of energy, and finally reveal the amazing shortcut that makes all of this high-speed flight analysis possible. All right, so our story doesn't kick off in a wind tunnel or a cockpit. Nope, it starts in a conference hall in Rome, where the entire future of aviation was about to get a massive, and I mean massive, upgrade. So picture this. It's 1935. The world's absolute best aerodynamicists are gathering for the Volta conference. And you've got to love the irony here. They flew there in planes that topped out around 130 miles an hour. But the topic of the conference? Flight at over 500 miles an hour. These folks were so far ahead of the curve, they were already calling the sound barrier a myth, and were having serious debates about supersonic, even hypersonic flight. This is also where Adolf Busemann first dropped the bombshell idea of the swept wing, which, as you know, became a total game-changer for high-speed drag. As one of the attendees, Jakob Ackert, put it years later, this conference was the moment a whole new field of science basically crashed the party. To even think about these new speeds, engineers realized they couldn't just focus on lift and drag anymore. They had to start thinking about energy. They had to learn the secret language of thermodynamics. So, why is energy suddenly the star of the show? Let's make this super intuitive. We'll do a little thought experiment, which I like to call the hand out the window test. Okay, you know this one. You're in a car, going about 65 miles an hour. You stick your hand out the window. You feel the air pushing on it, right? You feel the force. Now let's crank it up. Imagine you're in a jet going 10 times faster, 650 miles an hour, and you could stick your hand out. You wouldn't just feel force. You would feel an absolutely catastrophic, disastrous amount of energy. The air itself transforms into this incredibly powerful thing.
And that right there is the key idea. At high speeds, the kinetic energy packed into the moving air is just so enormous that it completely changes how the air itself behaves. We can't treat it like a simple, gentle fluid anymore. We have to treat it like a source of immense energy.
We've got a name for this new reality. We call it compressible flow. See, at low speeds, we can get away with pretending that air density is constant. But at high speeds, that energy squishes and stretches the air, and its density starts changing all over the place. This is a whole new ballgame, a completely different world of physics. And to play in this world, we're going to need a whole new toolkit.
So, how in the world do you analyze this high-energy, high-speed flow? Well, this is where thermodynamics steps in. It's not just a boring college subject, it's the essential toolkit. It gives us the language and the equations we need to master compressible flow.
The very first tool is a really clever simplification. We decide to treat air as a perfect gas. Now, this is just an ideal model, right? We basically assume the air molecules are pretty far apart, so we can ignore the tiny little forces between them. And why do we do that? Because it lets us use this beautiful, simple equation right here to connect pressure, density, and temperature. This little assumption is the bedrock for almost all high-speed analysis. Okay, so to track the energy in our perfect gas, we need to know 2 key properties. First is internal energy. That's just the sum of all the chaotic energy of the molecules themselves. You know, zipping around, rotating, vibrating. The second one is enthalpy. A great way to think of enthalpy is as a total energy package. It's the internal energy plus the energy the flow needs just to take up space, which is tied to its pressure. It's just a more complete way to keep track of all the energy in a moving fluid. Now, to really get a feel for the kind of energy we're talking about, let's figure out how much is just sitting in the air in a normal room. First, you calculate the mass of that air. For a standard-sized room, it's about 136 kilograms, or roughly 300 pounds.
Then use a simple thermodynamic formula to find the internal energy packed into every single kilogram of that air.
And when you run the numbers, it is absolutely staggering. The totally still, quiet air in just one room contains over 29 million joules of internal energy. To put that in perspective, that's about the same energy as a car crashing at highway speeds. And it's just there, locked away in the random motion of air molecules. That's the baseline energy we have to deal with even before the plane starts moving.
So we've established that there's this massive amount of energy all around us. But how does it behave? How does it move? Thermodynamics gives us two fundamental laws that are basically the ultimate rules of the road for energy. The first law is all about conservation. You can think of it as simple energy accounting. It just says that energy can never be created or destroyed, only moved around or changed from one form to another. So any heat you add to a system, plus any work you do on it, has to show up as a change in its internal energy. That's it. Simple.
But there's a problem. The first law, on its own, is incomplete. According to the first law, it would be totally fine for your hot coffee to get even hotter by sucking heat out of the cold air around it, just as long as the total energy stays the same. But we all know from, living in the real world, that never happens. Heat only flows one way, from hot to cold. The first law doesn't tell us anything about direction.
And for that, we need the second law. This is the law of direction. It's the universe's arrow of time. It introduces this incredibly important new property called entropy, which is, at its heart, a measure of disorder or randomness. And the second law says that in any real process, the total entropy of the universe can only ever increase, or at best, stay the same. It never, ever goes down. This is why heat flows from hot to cold. It's the fundamental rule that decides which way any energy process is allowed to go. Okay, so now that we have these two incredibly powerful laws in our back pocket, we can finally unlock the engineer's secret weapon, a really practical shortcut that comes directly from all this abstract theory.
So let's get down to it. How does knowing about things like entropy and internal energy actually help an engineer figure out what the pressure and temperature are doing over a real supersonic wing? How do we make this stuff practical?
Well, we do it by defining a perfect, ideal scenario. We call it an isentropic process. Isentropic just means constant entropy. Think of it as a perfectly efficient process. It's adiabatic, which means no heat leaks in or out, and it's reversible, which means there's absolutely no friction. It's the smoothest, most perfect transformation of energy you can imagine. And here's the magic. Assuming a process is isentropic allows us to combine those two laws of thermodynamics into this powerful set of relationships. Now, don't worry about the Greek letters. Focus on what this actually does. It ties pressure, density, and temperature together in a fixed relationship. If you know what's happening to any one of them, you can instantly calculate the other two. It's an incredible shortcut. And I know what you might be thinking. Okay, but that's a perfect case. The real world isn't perfect. But here's the real secret. As this quote explains, for most of the air flowing over a wing, everything outside that super thin, sticky layer right on the surface, the flow behaves almost perfectly isentropically. The losses from friction are just tiny. And that is the key that unlocks everything. The isentropic assumption gives us a fantastically accurate shortcut for almost the entire flow field around an aircraft. This powerful relationship is what gave those brilliant scientists at the Volta Conference the confidence to predict the future. They had the language, they had the tools to see how air would behave at speeds nobody had ever flown.
Of course, this all leads to a really fascinating question. If isentropic flow is the perfect case, what happens in those spots where the flow is far from perfect? What happens when the energy changes so violently and so abruptly that it becomes irreversible and entropy just skyrockets? Well, that's when you get shockwaves. But that is a story for another explainer.